Venus takes 243 Earth days to rotate once on its axis. Earth does it in 24 hours. Mars is similar to Earth. Jupiter, the largest planet in our system, spins so fast it completes a rotation in under 10 hours. But Venus is different. All Venus, a single day is longer than its entire year. It takes about 225 Earth days to orbit the Sun, yet 243 days to turn once. That alone should make you uncomfortable. But the real shock is not the speed. It is the direction. Venus rotates backwards. If you look down at the solar system from above the North Pole, the Sun spins counterclockwise. The planets orbit counterclockwise. And almost all of them rotate counterclockwise as well. They share the same signature, the same inherited motion from the cloud that formed them, except Venus. Venus goes the other way. If you could stand on its surface, ignoring the crushing pressure and the extreme heat, you would watch the sun rise in the west and set in the east. Something happened to this planet. Something powerful, violent, or incredibly patient. And the truth is, we still cannot say with certainty what it was. Before we can understand what went wrong with Venus, we have to understand what right is supposed to look like. In physics, you do not start with the anomaly, you start with the rule. Imagine a vast cloud of gas and dust floating in interstellar space, light years across. Cold and dark, this cloud is not perfectly still. Somewhere within it there is a tiny, almost imperceptible rotation. Maybe it was disturbed by a nearby supernova. Maybe a passing star gave it a slight nudge. The cause does not matter. What matters is that there is some angular momentum present. Even a small amount is enough. Now gravity begins to act. The cloud slowly collapses inward under its own weight. As it contracts, something remarkable happens. It spins faster, not because an external force is adding energy, but because of one of the deepest conservation laws in all of physics, the conservation of angular momentum. Angular momentum is the product of how fast something rotates and how its mass is distributed. When the cloud shrinks, its mass moves closer to the center. Its moment of inertia decreases. And because angular momentum must remain constant in the absence of an external torque, the rotation rate increases. You have seen this before. A figure skater pulls in her arms during a spin and she turns faster. She did not push against anything. She simply reduced her moment of inertia, and the conservation law did the rest. The collapsing cloud behaves the same way. As gravity pulls the material inward, the rotation speeds up. The faster spin flattens the cloud into a rotating disk. Material near the equator has more angular momentum and resists falling straight in, so it spreads outward into a thin, wide structure called a protoplanetary disk. At the center, most of the mass accumulates and forms the sun. Around it, within that rotating disk, dust grains collide and stick together. Pebbles become rocks. Rocks become planetesimals. Planetesimals merge into protoplanets. All of this material is moving in the same direction, counterclockwise. When viewed from above, the North Pole of the forming system, that direction is not random. It is inherited from the original rotation of the cloud. As planets grow by accreting material from the disk, they absorb not only mass but angular momentum. The spin of each planet reflects the overall motion of the disk from which it formed. The expectation, therefore, is simple and powerful. Planets should orbit in the same direction as the disk. They should rotate in that same direction as well. The sun should spin that way. The planets should orbit that way. and their daily rotation should carry the same signature. This is not just an elegant theoretical picture. We can observe young stars surrounded by protoplanetary disks in distant star-forming regions. Telescopes reveal flat, rotating structures with gaps carved by forming planets. The physics works. The conservation of angular momentum is not a suggestion or a convenient assumption. It is a tested principle that governs systems from spinning tops to galaxies. If nothing applies a significant external torque, the total angular momentum of a system remains constant. That is the baseline. That is what right looks like. Now consider what it would take to reverse the rotation of a planet. A planet is not a lightweight toy. It is an enormous rotating body with a mass measured in sextillions of kilograms. To change its spin direction, you must apply a torque. Either you do it violently and quickly, delivering a massive impulse that alters the angular momentum in a short time, or you do it gradually, applying a smaller torque consistently over billions of years. There are no other options. Angular momentum does not casually flip sign. It does not spontaneously reverse. It must be transferred, redistributed, or countered by an external influence. When we look at most of the solar system, we see the family resemblance clearly. Earth rotates counterclockwise. Mars rotates counterclockwise. Jupiter rotates counterclockwise. They orbit in that same direction. The pattern is overwhelmingly consistent with the original rotating disk model. That consistency is precisely why Venus stands out. If every other child on the carousel is moving one way and one child is moving the opposite way, you do not assume the carousel changed direction. You assume something happened to that one child. So the expectation is clear. A planet forming from a rotating protoplanetary disk should inherit that direction of motion. If Venus does not, then some torque must have intervened. Either a sudden catastrophic event delivered a powerful change to its angular momentum, or a long and persistent process gradually altered its spin over immense stretches of time. Those are the boundaries set by physics itself. That is the framework within which any explanation must operate. For thousands of years, human beings have looked up at Venus. It is one of the brightest objects in the sky, sometimes visible at dawn, sometimes at dusk. The ancient Babylonians tracked its motion. The Greeks thought the morning star and the evening star were two different objects before realizing they were the same planet. We have been observing Venus for most of recorded history, and yet we did not know which way it was spinning until 1962. That alone should tell you how deceptive this world is. The reason is simple and brutal. Venus is hidden behind the thickest atmosphere of any rocky planet in the solar system. The surface pressure is about 93 times that of Earth. That is comparable to being nearly a kilometer under the ocean. The temperature at the surface is around 465 degrees Celsius, hot enough to melt lead. The atmosphere is composed of roughly 96% carbon dioxide, with nitrogen making up most of the rest, and clouds of sulfuric acid floating high above. Those clouds are completely opaque to visible light. If you point an optical telescope at Venus, all you see is a bright, featureless white disk. There are no surface markings to track, no continents, no craters, no shadows drifting across a landscape, just a glowing blank mask. In the 17th century, Giovanni Cassini attempted to measure Venus's rotation. He believed he detected features moving across the surface and estimated a rotation period of less than a day. He was wrong by a factor of about 240. Other astronomers tried in the centuries that followed. Some assumed Venus must rotate in roughly 24 hours, like Earth. Others proposed periods of several weeks. All of them were guessing in the dark. The planet gave nothing away. It is remarkable to realize that by the time humans split the atom and built jet aircraft, we still did not know the length of a day on the planet next door. The breakthrough did not come from better lenses. It came from radar. In the early 1960s, scientists began bouncing radio waves off Venus. Radar does not care about visible clouds. Radio waves can pass through the dense atmosphere, strike the solid surface, and reflect back toward Earth. When that reflected signal returns, it carries information about motion. This is where the Doppler effect becomes crucial. If part of the planet's surface is moving toward us as it rotates, the reflected radar signal from that region will be shifted to a slightly higher frequency. If part of the surface is moving away from us, the frequency will be slightly lower. By measuring the spread in frequencies across the returning signal, scientists can determine how fast the planet is rotating and in which direction. It is an elegant method. You do not need to see mountains or valleys. You only need to measure tiny shifts in radio frequency. The side rotating toward Earth produces a higher frequency reflection. The side rotating away produces a lower frequency reflection. The asymmetry between the two reveals the direction of spin. When teams at the Jet Propulsion Laboratory and elsewhere performed these measurements, the results were startling. Venus was not rotating quickly. It was rotating extraordinarily slowly, taking about 243 Earth days to complete one turn. And even more shocking, it was rotating in the opposite direction from what most scientists expected, retrograde backwards relative to the majority of the solar system. When Richard Goldstein published these findings in 1964, some astronomers suspected an error. The number was so extreme that it felt implausible, but repeated radar measurements confirmed it. The data were solid. Venus truly rotates more slowly than it orbits the Sun, and it does so in the reverse direction. There's also a subtlety here that matters. By astronomical convention, the north pole of a planet is defined by the right-hand rule relative to its orbital motion. By that definition, Venus's axis is tilted about 177 degrees. It is almost completely upside down, only 3 degrees away from being fully inverted. You can describe the situation in two equivalent ways. You can say Venus rotates backwards, or you can say Venus is nearly flipped over and rotates in what would otherwise be considered the normal direction. Mathematically, the two descriptions are identical, physically. However, they suggest different histories. Was the spin reversed, or was the entire planet toppled? That distinction transforms a curiosity into a forensic question. We are no longer just asking how fast Venus spins. We are asking what event or process altered its angular momentum so dramatically that it ended up nearly inverted and rotating opposite to its siblings. And the only reason we can even pose that question is because radio waves pierced through a veil of acid clouds in 1962 and revealed what the visible light had hidden for centuries. If we are going to accuse a suspect, the most dramatic one steps forward first. A giant impact. Early in the history of the solar system, nothing was calm or orderly. The planets were not yet finished products moving along stable paths. They were still growing, still colliding, still clearing out debris from the rotating disk that formed them. Large protoplanets, some the size of Mars, wandered through the inner solar system on unstable orbits. Collisions were not rare accidents. They were part of the construction process. We believe Earth experienced one of these colossal impacts. A Mars-sized body, often called Theia, is thought to have struck the young Earth about 4.5 billion years ago. The collision was so violent that it blasted molten rock into orbit. That debris eventually coalesced into the moon. The evidence for this is not speculative storytelling. The isotopic composition of lunar rocks brought back by Apollo astronauts closely matches Earth's mantle. The chemistry reads like a fingerprint. Something enormous hit Earth and left a permanent mark in the sky. If such an event could reshape Earth, why not Venus? A sufficiently large impact could alter a planet's angular momentum in a single stroke. Picture a spinning top on a table. If you strike it from the side with enough force, you can knock it over. It may end up spinning with its axis inverted from an external perspective that looks like a reversal. Alternatively, a massive collision could slow the rotation dramatically, bringing it nearly to a halt, and then the residual torques in the system might allow it to begin rotating in the opposite direction. Either way, the mechanism is clear. A powerful torque applied over a short time can change a planet's spin state. This explanation has an immediate appeal. It is violent, decisive, and consistent with what we know about the early solar system. Statistically, it would be surprising if Venus never experienced a large collision. The inner planets were assembled in a chaotic environment. Impacts were common. So it is tempting to say that Venus simply drew the short straw. It was hit in just the wrong way, at just the right angle, and its rotation was flipped. Case closed. But when you look closer, problems appear. When Earth was struck, we gained the moon. A dramatic, visible consequence of the event. Venus has no moon. Not a small captured asteroid. Not a fragment. Nothing. If a giant impact reversed Venus's spin, where is the debris? Where is the evidence orbiting overhead? Some researchers argue that a nearly head-on collision would not eject much material into orbit. The energy would go into heating and deforming the planet rather than flinging fragments into space. Others suggest that debris might have formed a temporary disk but existed inside Venus's synchronous orbit. Because Venus rotates so slowly, the synchronous distance is far from the planet. Material inside that boundary would spiral inward due to tidal forces and eventually fall back onto the surface. Any moon that formed might have been short-lived and then reabsorbed. Notice what is happening here. We are adding layers of explanation to preserve the impact hypothesis. The impact was head-on, or the debris fell back, or a second impact destroyed a first moon. Each addition makes the story more flexible, and flexibility is dangerous in science. If a theory can accommodate almost any outcome, it becomes difficult to test. Recent computer simulations show that a wide range of impact scenarios can produce a rotation period similar to Venus's current state. Large impactors, smaller ones, oblique angle, near direct hits. Many combinations appear to work, but when too many scenarios fit the data, the theory stops narrowing the possibilities. It describes what could have happened, not what actually did. There is also the subtle issue of the 177-degree tilt. Did an impact reverse the spin direction while leaving the axis orientation mostly intact? Or did it physically topple the planet nearly upside down? These are not identical processes. They would redistribute energy and angular momentum differently within the interior. Without detailed knowledge of Venus's internal structure and composition, we cannot distinguish between them. The giant impact remains a plausible suspect. It operates within the laws of physics. It is consistent with the violent youth of the solar system, but plausibility is not proof. Unlike the Earth-Moon system, Venus offers no clear forensic trace, no orbital companion carrying isotopic testimony, no obvious scar in the form of a debris field. We are left with a mechanism that can explain the rotation, but we do not yet possess the fingerprint that ties the crime to the culprit. If the giant impact is the dramatic suspect, the second suspect is quieter, slower, and in many ways more elegant. It does not rely on a single catastrophic event. It relies on tides, not ocean tides, because Venus has no oceans. But gravitational and atmospheric tides acting over billions of years. To understand this, we begin with the sun's gravity. Venus is closer to the sun than Earth, close enough that the sun exerts a significant tidal force on the planet. Gravity does not pull equally on every part of a body. The side facing the sun feels a slightly stronger pull than the far side. This difference stretches the planet slightly, creating a tidal bulge along the line connecting Venus and the sun. The deformation is small, but it is real. Now imagine Venus rotating. If there were no internal friction, the bulge would always point directly toward the sun. But Venus is not a perfectly rigid, frictionless sphere. Its interior resists motion. As the planet rotates, the tidal bulge is dragged slightly ahead of the Sun-Venus line. It cannot respond instantly because the material inside the planet dissipates energy as heat. This misalignment matters. The sun's gravity pulls on that displaced bulge and creates a torque. That torque acts as a brake. It removes rotational energy from the planet and gradually slows the spin over long periods of time. Gravitational tidal dissipation tends to drive a planet toward tidal locking, a state where one side permanently faces the star, as the moon does to Earth. Mercury is caught in a related but slightly different resonance because of its orbital eccentricity. If gravitational tides were the only effect, Venus might have ended up tidally locked to the sun. But Venus has something Earth does not, at least not to the same extreme. It has an enormous, dense atmosphere. The sun heats this atmosphere unevenly. The day side receives intense solar radiation, while the night side cools. Because the atmosphere is so thick and dominated by carbon dioxide, it has significant thermal inertia. It does not heat and cool instantly. The hottest region in the atmosphere is not located exactly at the point directly beneath the sun. It is shifted slightly due to the planet's rotation and the slow response of the gas. This shift creates a second bulge, not in the solid body, but in the atmosphere. A region of higher pressure and mass concentration forms in a location that lags or leads the subsolar point depending on the dynamics. The sun's gravity pulls on this atmospheric bulge just as it pulls on the solid one. But here is the crucial detail. The torque generated by the atmospheric bulge can act in the opposite direction to the torque generated by the solid body tide. Instead of breaking the rotation towards synchronous locking, it can push the planet away from that state. You now have a tug-of-war. The solid body tide tries to slow Venus and align one face permanently toward the sun. The thermal atmospheric tide, generated by uneven heating and delayed thermal response, pushes in the reverse direction. Imagine floating in a lazy river where the current pulls you one way while a steady wind pushes you the other. If one force dominates, you drift in that direction. But if they nearly balance, you can reach a state where the net motion becomes very slow or even reversed relative to the initial flow. Mathematical models developed over the past several decades show that when both torques are included, along with internal dissipation within the mantle and possible interactions at the core mantle boundary, the system does not evolve randomly. It tends to settle into one of several stable rotational states. Think of a marble rolling across a hilly landscape. No matter where you release it, it eventually settles into a valley for Venus. Calculations suggest there are 4 such valleys. 2 correspond to prograde rotation with periods of roughly 77 days. 2 correspond to retrograde rotation with periods near 243 days. The retrograde states appear to be more stable under a wide range of conditions. In this picture, Venus's backward rotation is not an accident, it is an attractor, a natural resting place in the dynamical landscape defined by gravitational and atmospheric tides, even if Venus began with a different rotation rate, as long as certain conditions were met. The combined torques could gradually steer it toward the slow retrograde state we observe today. No single catastrophic blow is required, just the patient, relentless action of the sun's gravity interacting with a thick, superheated atmosphere over billions of years. This explanation has a powerful appeal because it relies on forces we know are acting right now. The sun is still pulling. The atmosphere is still heating and shifting. The torques can be calculated, yet it is not without its own uncertainties. The outcome depends on the initial rotation rate and the details of internal dissipation. But unlike the giant impact hypothesis, this model does not require an unobserved ancient collision. It suggests that Venus may simply be obeying the long-term consequences of its environment, evolving naturally into the backward spinning world we see today. The atmospheric tide model is elegant, but it has a weakness. It depends on where Venus started. If the planet originally rotated very rapidly, completing a turn in just a few hours, as many young planets likely did, then the braking effect of gravitational tides would have been strong, and the atmospheric torque might not have been powerful enough to reverse the spin within 4.5 billion years. Some calculations suggest that for the atmospheric tides to successfully drive Venus into its current retrograde state, the planet's early rotation period needed to fall somewhere between roughly half a day and 3 days. If it started much faster than that, the atmospheric torque would have been fighting a losing battle. This opens the door to a hybrid scenario. Perhaps Venus did experience an impact, but not a catastrophic one that completely flipped the planet. Instead, imagine a moderate collision, not large enough to leave obvious debris or create a lasting moon, but sufficient to slow the rotation from a rapid initial state down to a few days. That reduction in spin would change the balance of torques. Once the rotation slowed into the critical range, the atmospheric tides could take over and gradually push the planet into the retrograde attractor. In this picture, the impact did not reverse Venus. It prepared the conditions. The atmosphere finished the job. This combined explanation may not be as dramatic as a single colossal event, and it may not be as aesthetically simple as pure tidal evolution. But nature rarely conforms to our preference for clean narratives. Multiple processes often overlap. One mechanism sets the stage. Another delivers the final outcome. The laws of physics do not care whether the story feels elegant. They only care about forces, torques, and time. There's another reason to take the atmospheric influence seriously. Venus's rotation is not frozen in time. It is still changing. In the early 1990s, NASA's Magellan spacecraft mapped the surface of Venus using radar. By tracking how recognizable surface features moved beneath the spacecraft over several years, scientists calculated the rotation period with extraordinary precision. Approximately 243,0185 Earth days. 16 years later, the European Space Agency's Venus Express mission observed the surface again using infrared techniques capable of peering through the clouds. When researchers compared the new data to the Magellan maps, they found that surface features had shifted by up to about 20 kilometers from where they were expected. The inferred change corresponded to a difference of several minutes in the rotation period over just 16 years. For a planet, that is astonishing. Earth's rotation changes by milliseconds per century, largely due to tidal interactions with the moon. Venus appears to change by minutes over decades. Something is actively exchanging angular momentum with the solid body. The prime suspect for these shorter-term fluctuations is the atmosphere itself. Venus's upper atmosphere exhibits what is known as superrotation. High-altitude winds circle the planet at speeds approaching 360 kilometers per hour, completing a full circuit in roughly 4 Earth days. Meanwhile, the surface below turns once in 243 days. The atmosphere is effectively racing around a nearly stationary planet. This enormous mismatch implies friction and angular momentum transfer between the atmosphere and the surface. When atmospheric circulation intensifies, it can extract angular momentum from the solid planet, slowing the rotation slightly. When circulation weakens, some of that momentum may be returned. If Venus undergoes long-term atmospheric cycles, lasting decades or longer, the observed variation in rotation period could reflect one phase of a broader oscillation rather than a permanent trend. The problem is that we have only 2 well-separated data points. We do not yet have a continuous time series. There is also a curious numerical coincidence. Every time Venus makes its closest approach to Earth, approximately every 584 days, it presents nearly the same face toward us. 5 Venusian solar days fit almost perfectly into that interval. The match is not exact, but it is strikingly close. Some researchers have speculated that because the net torque on Venus may be small when gravitational and atmospheric tides nearly cancel, even the weak gravitational pull of Earth during close approaches could influence the rotation state. Most modern analyses suggest that Earth's effect is likely too small to maintain a true resonance. Still, the near alignment adds another layer of intrigue. In the hybrid view, Venus's backward rotation is not the result of a single dramatic event or a single slow process. It may be the outcome of overlapping influences. An early impact adjusting the initial spin, atmospheric tides shaping the long-term evolution, and ongoing atmospheric dynamics continuing to modulate the rotation even today. Venus is not a static relic. It is an active system, still responding to forces, still redistributing angular momentum, still evolving. If we want to move beyond plausible stories and actually solve this case, we need better evidence. Right now, we are trying to reconstruct 4.5 billion years of rotational history from a handful of measurements and a few theoretical models. That is not enough. The first thing we need is a clear understanding of Venus's interior. Is the core solid or liquid? Does it have a solid inner core surrounded by a liquid outer core like Earth? How large is it relative to the mantle? What is the density profile from the surface to the center? These details matter because tidal dissipation depends strongly on internal structure. The way a planet responds to gravitational torques is controlled by how energy is absorbed and redistributed inside. If the core and mantle are partially decoupled, they may exchange angular momentum in complex ways. If the core is entirely solid, the response could be different. Without knowing the internal structure, we are guessing at key parameters in the tidal models. How do you measure the inside of a planet you cannot even see clearly through its atmosphere? One method is precise Doppler tracking of an orbiter. Tiny variations in the spacecraft's motion reveal subtle changes in the planet's gravitational field. From those variations, scientists can infer the distribution of mass inside. Even better would be a seismometer on the surface. Seismic waves generated by quakes or impacts travel through the interior and carry information about layering and composition. That is how we mapped Earth's core and how we are beginning to understand Mars through missions like InSight. But placing and maintaining a long-lived seismic station on Venus is extraordinarily difficult. The surface temperature is hot enough to melt lead. The pressure is crushing. The atmosphere is chemically hostile. Electronics degrade rapidly. Any lander must survive conditions that destroy conventional hardware in hours. The second requirement is long-term, high-precision monitoring of Venus's rotation. 2 snapshots separated by 16 years are not sufficient to determine whether the planet's spin is drifting steadily, oscillating over decades, or fluctuating chaotically due to atmospheric dynamics. We need a continuous time series spanning decades. That could be achieved through dedicated radar observations from Earth combined with repeated orbital mapping missions. With enough data points, patterns would emerge. We could distinguish between short-term atmospheric exchanges of angular momentum and deeper secular trends driven by tidal evolution. The third and most ambitious goal is sample return. If a giant impact played a significant role in altering Venus's spin, the crust and mantle might contain isotopic signatures of that event. On Earth, lunar samples reveal mixing between Earth's mantle and the impacting body. Similar chemical fingerprints on Venus could point toward past collisions. Ratios of certain isotopes, particularly those associated with core-forming elements, could reveal whether foreign material was incorporated into the planet during its early history. But retrieving samples from Venus is far more challenging than from Mars. A spacecraft would need to land, drill into rock at 465 degrees Celsius under 93 atmospheres of pressure, seal the material, and launch it back through a dense carbon dioxide atmosphere. The engineering demands are extreme, yet they are not fundamentally impossible. History shows how unforgiving Venus can be. The Soviet Venera missions of the 1970s and 1980s managed to land several probes. The early attempts were crushed before reaching the surface because engineers underestimated the atmospheric pressure. Later landers survived for minutes, in some cases a little over 2 hours, transmitting images of a flat, rock-strewn landscape under a dim orange sky before their systems failed. Those brief transmissions are the only direct surface data we possess. They demonstrate both the feasibility and the difficulty of operating there. To truly resolve the mystery of Venus's rotation, we must combine interior measurements, long-term rotational tracking, and geochemical analysis. Each line of evidence would constrain the models. Together they could narrow the range of plausible histories. Until then, we remain in the realm of informed hypotheses. The tools to answer the question are within reach of future missions. What is required is patience, investment, and the willingness to pursue data rather than narratives. When you step back from the details of torque calculations and orbital mechanics, Venus teaches something larger about how science actually works. The solar system is often presented as a clean, orderly machine. A rotating cloud collapses. Planets form in a disk. They orbit in the same direction. They rotate in the same direction. Conservation laws hold everything together. That picture is mostly correct. But mostly correct is not the same as complete. The gaps between expectation and observation are where the real discoveries wait. Venus spinning backward is not a violation of physics. It is a reminder that physics operates through layers of interacting processes, not simple slogans. Look at the broader pattern. Uranus is tilted so dramatically that it appears to roll along its orbit, its axis nearly parallel to the plane of the solar system. Something extraordinary must have happened there as well. Neptune's largest moon, Triton, orbits in the opposite direction of Neptune's rotation, almost certainly a captured object from elsewhere. Mercury is not fully tidally locked to the Sun, but trapped in a 3-to-2 resonance because of the subtle interplay between tidal forces and orbital eccentricity. Each of these cases is an exception to the simplest version of the formation story. Each forces us to refine the model. The deviations are not inconveniences. They are clues. Venus may be the most striking example because it is so similar to Earth in basic physical properties. Its size is comparable. Its mass is comparable. Its density suggests a similar overall composition. It formed from the same protoplanetary disk in nearly the same region around the Sun at nearly the same time. If you were handed only those numbers and asked to predict its state today, you might imagine oceans, weather systems, perhaps even life. Instead, Venus is a world where the surface temperature can melt lead, where carbon dioxide dominates the sky, and where sulfuric acid clouds obscure the horizon. And on top of that, it rotates backward. Somewhere along their shared history, Earth and Venus diverged catastrophically. Rotation plays a fundamental role in that divergence. The length of a day influences atmospheric circulation patterns. The Coriolis effect shapes winds and storm systems. The interaction between rotation and interior convection affects magnetic field generation. A slowly rotating planet distributes heat differently from a rapidly rotating one. A retrograde planet experiences sunrise and sunset in reversed directions, altering long-term climate cycles. While rotation alone does not determine habitability, it is part of a tightly coupled system of processes that shape a planet's environment. Understanding why Venus spins the way it does is not merely about curiosity. It is about understanding how similar starting conditions can lead to radically different outcomes. There is also a lesson about intellectual honesty. It is tempting to prefer the explanation that feels most satisfying. The giant impact story is dramatic and cinematic. The atmospheric tide model is elegant and mathematically rich. The possibility of subtle resonances adds a layer of intrigue. But the evidence we currently possess does not allow us to declare a single winner with confidence. To admit that is not a weakness. It is the foundation of real inquiry. Science advances not by pretending uncertainty does not exist, but by confronting it directly. The willingness to say we do not yet know keeps the investigation alive. Anomalies force us to sharpen our tools. If everything behaved exactly as expected, our models would remain simplistic and untested. Venus challenges our assumptions about planetary evolution. It pushes us to measure more precisely, to simulate more carefully, to explore more boldly. Somewhere in the interaction between impacts, thesis, atmospheric dynamics, and internal structure lies the full story of its backward spin. When that story is finally reconstructed, it will not overturn the laws of physics. It will deepen our understanding of how those laws play out in complex, evolving systems. Until then, Venus continues to turn slowly in the opposite direction, a reminder that nature is often more intricate than our first explanations. The rule gives us a starting point. The exception teaches us how much more there is to learn.